This piece requires that you've actually gone through round one, round zero, phase one of the Yeller promotions simulation that we started way back in module one. So if you haven't done that yet, just stop this video, go back to module one, review those requirements, all the separate pages about the Yeller promotions, watch the videos, read through the questions, answer the questions in the assignment, and then come on back and we'll proceed. Even if you have done that, it probably won't hurt for you to go back and review the videos one more time just to get refreshed. And as a little bit of a refresher, Yeller Promotions makes a fan flapper device. So it's a noisemaker to generate more enthusiasm and craziness in a place like the Horseshoe for Ohio State. It could be any stadium anywhere. These could be reconfigured for any letters to represent your local team. But in Ohio, we have this thing where people shout out OH and your typical response is IO. And so we got half the stadium waving the OH flapper, making noise, hollering OH, and the other half flapping the IO in response until we get this rising crescendo of motivation and the fans go wild for the team. When we do this, there are a lot of roles and a lot of rules in this. You can pause on this and review these if you want, but typically we have people providing paper to the workers who then will write letters on the cards, who will then transfer them by fork truck or courier or whatever to the clipping department, where the clippers will take individual cards out of the stack and align them and put a paper clip on them. And then building in a batch of 5, they'll transfer that to stapling. Stapling will put a staple in it, remove the clip, and then pass it off to quality usually. And then quality will inspect it, rework it if it needs it, and then go ahead and put it out to the customer. When I've got a bigger crowd, I put a maintenance team in place. I might have a separate accountant. I might have a separate plant manager who's supposed to lead this. And we try to have a couple of folks be the industrial engineer to do the time studies, to count and capture the process times, the total lead time. Go back and look at the videos and see what roles you can pick out. But let's look at the performance now of that first round. Now, the videos that you saw may or may not be associated with this particular data set, because I have done this simulation literally all over the world. And what you're going to see, this is typical performance of the first round. And what we've got, as you can see, I've got an inventory count, work in process, for each one of the working stations. There's the O writer station, the H writer, the I writer, the clipping, stapling, and quality. All those workstations. The I here up at the top, this stands for the initial inventory level. So when we started the timed production run, this is how much inventory was in the system. So each of the 2 O writers had 5 cards, the H writer had 5 cards, the I writer had 5 cards. There were 20 cards, 4 different stacks, batches of 5 at clipping, and then 20 cards, or 4 batches of 5 only. This time they're configured into a semi-final product that just needs to be stapled. And then stapling sends them on to quality. When we, up to this point, we're counting individual cards. When they get a staple in it, we count the unit, because that is a sellable produced unit. As you can see, we get some inventory piling up at clipping and in stapling, because anytime your ending inventory level is higher than your initial inventory level, something is slowing your system down. We want to find those things. Here we've got a total work in process remaining after the production run of 157 cards. We ran for 3 minutes, 180 seconds, and in this case, this team produced 21 units. Doing the math, 180 divided by 21, that's 8.8 seconds per unit. So that's our cycle time. Uh, the average time elapsed for a product to leave a system. Our cycle time, average of 8.6 seconds. Our total throughput time, we couldn't really tell. We would have an engineer mark a set of cards, and then when they're delivered to the writer, they start the clock, and they follow it through the writing process, the clipping process, the stapling process, and when it's finished with quality and they hand it to the accountant, they stop the clock. That gets us the total throughput time. In this case, we waited 30 seconds for the system to work to make sure that things were going the way they were supposed to be, and then we launched a marked set of cards. And that marked set of cards never made it through. So that's how we come up with a little bit more, somewhere more, something in excess of 150 seconds. We also had 14 people on this particular case, and we have this last number. This is we call it a productivity index, but it's not really a conventional productivity measure. What we're trying to do is we're trying to see the total amount of time, total amount of person hours that we burn to produce one unit. So the colleagues I worked with when we designed this, they thought this was a pretty decent measure that we want to drive down. The lower we can make this, the better off we're going to be. And so if you look at this spreadsheet, as a lean practitioner and as a leader in an organization, you should be able to look at this spreadsheet and say where the problems are. So that's my question. Where are those problems? We can see pretty well clipping is going to be a problem. Clipping, clearly a bottleneck. Why are they unable to keep up? If you look at them in the video, they don't seem to be taking any breaks, so they're always working. So why is clipping a bottleneck? Why do we have the clip anyway? A lot of groups say, hey, that's just dumb to have the paper clip there. Well, I will have to tell you that the critical step in the process to get the right kind of sound from that flap means the cards have to be aligned just right. And that takes a little time to pull them off a stack, get them perfectly aligned, and then once you get them perfectly aligned, you want to preserve that alignment until you can get a staple in it. Because we have a transfer between clipping and stapling, or a transfer between writing and stapling, we installed this intermediate step, and we require a paper clip to preserve that alignment as those cards transfer or get transported to that final stop. That's going to be a requirement for the next several modules, okay? As we go through all these flow things, you're never going to be able to get rid of the clip. I'm just going to tell you that right now. You can't eliminate the paper clip until way at the end. As long as there's you can only eliminate the paper clip if there's absolutely no transfer, I'm setting something down for somebody else to pick up. Okay, so what other problems do you see? How about this one? Stapling. So it's easy for us to see that clipping is a bottleneck, but what if I told you that clipping is not the real bottleneck? Because the definition of a bottleneck is the operation with the longest cycle time. And depending on how we count, stapling actually has the longest cycle time because it has a changeover after every single batch. So it might be very quick stapling 5 sets, but then when we have to do the changeover, that's where we burn some downtime. It's actually longer than it takes the clippers to do their 5 batches, a batch of 5 cards. So the true bottleneck is hidden by the obvious problem at clipping. What about quality? Oh my gosh, we've got 22 cards in quality. That's 11 sets, 11 pieces of our product that we should be able to deliver. Why can't these guys keep up? What's taking them so long to do their work? What would we need to do to just eliminate quality? Because that's got to be one of our first steps, is how do we build quality in instead of trying to inspect it? I'll go ahead and give you an answer on this one. Quality is taking so long because the quality standard that they use is still moderately subjective. So there aren't detailed engineering drawings and specifications that we're trying to hold all the writers to. If we did, we might want to put some fixtures in place for those writing, or might just buy a printer so that each one of those printers can be the same. But for now, we're using people, and people are variable. Other problems, output. Output, we only got 21 cards, my God. In 3 minutes. That's less output than we expected, but what did we expect? How many did we expect? Nobody ever said we've got to be able to produce this many. And so we had no expectation. So I can't tell you if this is actually good or bad because I've got no gap. I've got no expected performance, and I've only got an actual performance. It sounds low, but if I don't have that expectation clear, I can't really tell you how bad this problem is. This, on the other hand, tells us a lot. This tells us it takes 120 seconds, 120 person seconds to produce a single unit. That's 2 freaking minutes. Now look at this simple device. If you had 2 cards and a pen and a stapler, how long would it take you to put this thing together? You'd be able to do it just like that. Certainly not 2 minutes. So we know there's just a ton of problematic stuff in this system. Again, that productivity metric, 2 minutes per. I am currently working, but before we get finished with module 14, the final round of this, I'm probably going to have some new measures on this because I've been playing with this and I want to scale it up a little bit. We also have some financial things. So total WIP, the value sitting on the floor. This is what we leave on the table after we've produced everything. A material cost of $157 based on $1 per card. We sell the finished unit for $5. And so there should be a pretty decent profit margin. If we got $2 worth of material plus a clip and staple and labor, we should be able to have at least $1 worth of profit somewhere. So we got a labor figure in there. It's reduced to seconds, so our cost is 0.0075 cents per second. And so that doesn't work out very well either. So that's why I'm going to play with the numbers a little bit. But when you've got that high WIP level and that low revenue level, that $105 of money coming in, you know you're going to have ugly cash flow. So why did the system perform like this? Now, this was very much a conventional system. So some of the characteristics and structures about conventional systems include a functional layout. So we put the O-riders together because that's a function. We put the clipping together someplace else because that's a function. We put the stapling together, and that's a function. And remember, our stapler simulates a large, expensive piece of equipment, not something that you can just move around very easily. This is something that you have to put a CapEx together. You have to do all the analysis and the cost benefits to determine whether or not you can even buy this thing. And then once you buy it and you install it, you've got 7 to 10 years to amortize it or depreciate it, and you've got to be able to get your output from that to pay it back. That's our conventional accounting system speaking. In other industries, in other places, okay, so think about, we put IT, all of those information technology guys together in a department. We put accounting all together in an apartment. We put HR all together in a department. In operations, we might have plastics or wood products or assembly or steel bending. We've got all of these different things. We put all the equipment that we need for all of those functions together. And so occasionally we'll have equipment that needs to be shared by several different product families. And whenever we have sharing, we're going to get into some problems. They run out of balance. We also have the structure is defined by routing. So because I've got all these functions all over the place, the only way I can really say, here's my production plan, is to say, let's take a batch and put it here, and then when it's finished there, we're going to move it over here. When it's finished there, we're going to move it someplace else, and it's going to follow a defined route through all the different functions that has to act on this product or service one way or another. So our process is simply a definition of the routing through our facility. And so you can imagine there is just tons of excess transportation and tons of excess motion. We also are going after economies of scale, which often is, well, it's just a myth. If we look at the individual unit cost of these things, that's going to be driven by so many different things. So because of the inefficiencies inherent in the system, the only way we can really benefit from scale is producing in larger batches. And the batch size is supposed to cover all the downtime, so we can say we're keeping people working and things like that. Put some effort into looking into economies of scale and batching. Why do we do it? Why is it comfortable? Why do we like it? And you'll see some pretty cool things. We also try to, we superimpose control systems instead of building control into these systems. Because it is defined by routing and there is so much moving around, we have to have some way to get a sense of control. And so we spend millions and millions of dollars on scheduling systems and millions of dollars on tracking systems. We put all kinds of financial controls and financial gateways into our metrics all through our system, all in an effort to give us a sense of control. When in reality, these systems are inherently out of control because they're just broad and out of balance and chaotic. And then it requires more management. And to manage a conventional mass manufacturing, mass production oriented system, management is kind of detached from the operations. So we let those people do the work, and I'm the boss and I'm going to come by. And so the bosses really don't know what's going on with the work. They probably don't spend much time out on the floor. And so it's a whole different philosophy of management, and it's been reinforced with performance appraisals, and it's been reinforced with the way we punish failure. It's been reinforced by the incentive systems that we put in place that can be manipulated or gamed by creative people. And we put all these in place, and it just reinforces everybody's need for compliance. If you step out of bounds, somebody's going to smack you back in, and that is the biggest cultural problem that we have. So with that in mind, what kind of performance would you expect? What kind of production lead time might we have? Remember, we're running in larger batches all through this system, so the production lead time is going to grow and grow and grow. Because we are staged in all these different places and we've got equipment that we want to bring material into as soon as it's available, we got a lot of work in process inventory. Lots of transportation, lots of handling, lots of handoffs, moving things 4, 5, 6 times between each one of these steps. Because it's not like we finish a job and we put it in the next queue. We finish a job, we put it in the warehouse. And then when this schedule for that next system calls for it, somebody's got to go fetch it, they got to go find it, they got to do the right thing, and then transport it in. When they're finished, it goes back to the warehouse. So it's all this back and forth and back and forth. Utilization is, you saw on our number, the productivity number is more of a utilization number than anything else, I guess. Um, it's extremely high. If it's over 100% utilization, we got a problem. Uh, what we run into problems is with leaders who intuitively calculate labor utilization. Um, there are leaders out there who want to see their people busy working, and they would be very happy in that conventional system because everywhere they look, people are actually working, and it always looks like they're busy. But what we really need to be focused on is what are we getting out the door? And then you could see that maybe they're working on the wrong things because we're not getting enough stuff out the door. Again, back to the control system, I won't say anything else about that. These typically take more space, lots of room, and lots of walking back and forth, lots of driving fork trucks back and forth, lots of wasted space. And because it takes so long to get something all the way through, if a customer has a custom order to submit, we've got to put it in the queue and it's got to be behind all this other stuff in the system. So it takes a long time for us to get a product to that customer. What we usually do in most cases is we expedite something for a customer who's special. So we'll do some work and we'll make it jump to the front of the line. And what does that do to the rest of the schedule? It blows it for the rest of the week or the rest of the month. And finally, how we measure performance varies greatly. We want to be able to find the right kind of performance measurement that really connects with the people that are doing the work and really gets us accurate information about the equipment that's doing the work so that we can do things like do more predictive and preventive maintenance on all the equipment, and so we can understand when we need to flex our workforce and move more people into a particular place, or when we need to stop working overtime and spread it out over a longer period. One of my worst experiences is when a company gets really, really busy during a week, or they get toward the end of the month and they've got a target that they want to hit. So everybody's just working crazy. They're working overtime, they're working the weekend and everything else. And then the next time it comes around, we don't have any work. And so we got to send people home. So we get all kinds of crazy stuff like that. Over the next few modules, we're going to be going through creating flow and fixing all those problems. So I hope you stick with us.